Hello friends, in this particular video we will learn the high frequency response of BJT amplifier, where we'll have to learn few different concepts and we'll have to apply these concepts to find out the higher cutoff frequency so that we can easily get the mid frequency range voltage gain, and also we can draw the complete frequency response of particular amplifier. So in this particular video we will learn with BJT, and in the next video we will learn the FET. So let's start with BJT amplifier. First we'll have to learn that what will be affected if I increase the frequency towards more and more higher side. See, as far as these capacitances are concerned, if I apply the very high frequency, so I know that Xc is equal to 1 upon 2 pi Fc. Okay, so if frequency increases, right, and tending towards infinity, then I will get to know that Xc will start decreasing and will tend towards zero value, right? And basically the fundamentals of CC1, CC2 and CE is such that they are used to couple the two stages of particular amplifier and bypass the particular resistance which is for the negative feedback. And as far as this particular three capacitances are concerned, you will get to know that this particular capacitances gets short, right? So it will form a short circuit if the Xc will be tending towards zero, so it will be having very less valued resistance, and ideally it will be short circuit, right? So ideally, as F is equal to infinity, then we'll be having Xcc1 is equal to 0, Xcc2 is equal to 0, as well as Xe is equal to 0, right? So if Xce is equal to 0, this capacitor will be replaced by short circuit, this capacitor will be replaced by short circuit, and this capacitor will be replaced by short circuit. Okay, that has no problem for my particular circuit, right? But there are such parameters there are such capacitors rather which are responsible at the higher frequency response, right? Higher side frequency response, and these particular capacitances are the intrinsic capacitances, or it is called as stray capacitances, right? So basically the terminal, this is B, this is C terminal, and this is E terminal. Okay, so B, E and C terminal internally have the capacitances. This is because if I draw the complete BJT form, then I'll get to know that this is the emitter part, right? This is the base part and this is the collector part, and in between I have the junctions. So basically these junctions forms the capacitances, right? So we'll get three kinds of capacitances. One is in between base and collector, one is in between collector and emitter as well, and in between the base and emitter as well. So we'll do the Namakaran for this particular capacitances as C, B, C, that is in between base and collector, CCE, that is in between collector and emitter, CBE, that is in between, this I'll write it in a small letter because we require that in a AC analysis as it's a function of frequency. So this is CBE. Okay, we got three capacitances. One is CBC, one is CBE, and another is CCE. Now let's look, if frequency is equal to infinity, what will be the effect on this particular BJT? BJT will get short circuited completely. E is connected to B, B is connected to C, C is connected to E as well, and everything is like Gopal Kala, right? So I can say that this BJT will get damaged, right? So I have to decide up to what particular value of frequency I have to get the particular value, higher value of voltage gain without damaging my BJT, that is nothing but the heart of my amplifier, right? So as far as BJT security is concerned, I have to design the higher frequency, right, higher cutoff frequency. So basically, to decide the higher cutoff frequency, CBC, CBE and CCE are responsible, right? More than that, we have the contact capacitances. Capacitances formed by the contact, that means nothing but the wiring capacitances. These wiring capacitances are at the input side as well as at the output side. So we term this as CWI at input side and CWO at output side. I'll purposely not draw these particular capacitances over here. It will do more and more khichadi here in this particular circuit. So to avoid that, we'll be having a separate AC equivalent model. So fantastic AC equivalent model we will draw, and then we'll get to know that how we will be getting FH1, FH2 and FH3 formed by the RC circuit. Okay, so we will first draw the AC equivalent circuit. This is purposely for higher frequency response. So we have to look at only the capacitances which are nothing but CBC, CBE and CCE, more or less at the input side and output side wiring capacitances as well. But we don't have to look for CC1, CC2 and CE, as at the high frequency they are getting shorted and I want that short circuit which is beneficial as far as the circuit is concerned. Okay, so let us see AC equivalent model for this particular circuit. For high frequency, we'll draw basic BJT AC equivalent. As far as the emitter is concerned, we will not draw the emitter resistance over here. This is because if CE gets shorted, I will be getting the resistance RE will be redundant and emitter directly connected to the ground. So we will say that this is ground, nice, this is R pi, this is GM V pi, okay, whereas this is your V pi, this is your V pi, okay. And I can say now we will first draw this complete RB, where RB is nothing but R1 parallel R2, capacitance CC1 is shorted and the resistance R signal is there, okay, and this is your input side. Simple. As far as, okay, fine, at the output side we will have to draw. As far as BJT is concerned, we'll not consider the RO, which is very high, will not consider in this particular circuit AC equivalent model, and this is your RC and directly connected to the VO. Now here we have to draw the particular capacitances that are nothing but the stray capacitances. Okay, so in between base and here we'll draw, this is base, this is collector and this is emitter. In between base and emitter, in between base and collector, sorry, I will be having the capacitance, that is CBE, sorry, CBC, collector base capacitance. Here we will be having another capacitance, that is CBE, okay, and also we will be having the wiring capacitances, that is nothing but CWI. Simple. Okay, as far as these input capacitances are concerned, it's over. As far as output capacitances are concerned, we will draw a small wiring capacitance, that is CWO first, and then we'll be also having one more capacitance, that is nothing but connected from C to E. Okay, so it looks like beautiful khichadi over here. So let's see this CCE. Okay, all done. Now critical part is this CBC. Okay, as far as this CBC is concerned, I cannot differentiate input and output of this particular AC equivalent model. Now the solution is, already we have learned Miller's theorem, right? So what we will do, we will remove this culprit CBC and we will take this CBC ka form at the input side of the BJT amplifier AC equivalent model and also at the output side of AC equivalent model, right, in a different way. So for that, obviously we have to have the knowledge about the ratio of output voltage to the input voltage over here. So we will say that this is nothing but, let's say, Vx and this is nothing but, we'll say, Vy. Okay, so we should know that what is Vy divided by Vx, that is nothing but the AV for Miller's theorem, Miller's calculation. Okay, so as far as the voltage is, input voltage for Miller's theorem Vx, output voltage for Miller's theorem is Vy, and we know that what is Zmi from Miller's theorem, right? So we'll say that from Miller's theorem, Zmi, what is Zmi? Zmi is nothing but Zi. Z, it's nothing but Z. Zf, I can say, that is nothing but the related with the reactive capacitive reactance of CBC, right? Z divided by 1 minus AV. Okay, as far as output Z is concerned, it is nothing but Zmo is equal to Z divided by 1 minus 1 upon AV. Simple. Okay, so as far as AV is concerned, we have to consider the negative sign of the AV as well, because this is your CE mode of BJT amplifier. So amplifier will work well in your CE mode as CE mode only. So I can say that this negative becomes positive, right? But we are considering not Z, here we have to consider the value of the capacitances directly. So what we will say, if as I can say that XC, here Zmi is in the form of capacitive reactance and Z is in the form of capacitive reactance itself. So XC is inversely proportional to the value of C. Agree with that? Yes. So if it is inversely proportional to the value of C, then I will be getting Cmi is equal to 1 minus AV into C, right? And here specifically we will write that it is CBC. So we will say that the value is nothing but CBC. So this is one of the input Miller's capacitance we have got. So to have to convert this value of CBC at the input side under consideration of AV, where AV is nothing but Vy divided by Vx. Okay, next we'll have to say that CMO, also we don't have to consider this particular factor parameter at the denominator, we'll have to consider in the numerator itself. So we'll say that 1 minus 1 upon AV into CBC. So these two values are very important as far as input and output capacitances are concerned. Here we have to get only two values of frequency. One is related to the input side and one is related to the output side, as your bypass capacitor always and always becomes short circuited as F tending towards infinity. Okay, so let us have the modified AC equivalent model in the form of parallel combination of R and C, so that we'll get two RC circuit. One is at the input side and another is at the output side. So we'll draw that particular circuit quickly so that So this is your modified equivalent, AC equivalent model for your BJT model. So in this particular case, we have to consider complete this RC circuit, that is first, and this complete RC circuit, here it is grounded obviously, and here I have to consider this complete RC network, that is second one, which will give you the higher cutoff frequency FH1 and FH2. Rather we can use it as FHI or FHO, right, input and output. So if we consider, we will say that what is nothing but this, all capacitances are in parallel. I can say that this CI is nothing but CMI plus CBE plus CWI. So CMI, that is Miller's input capacitance, plus CBE plus CWI. Okay, so whereas I can say the values of CBE and CWI will be given. If CWI is not given, then don't have to consider CWI. If how to calculate the value of CMI? So we'll write over here, CMI is nothing but 1 minus AV multiplied by CBC. Okay, again we'll have to consider that where the value of AV is nothing but Vy divided by Vx, whereas I have to consider that this is your Vy and this is your Vx, right? Many a times we consider this value of Vi and this value of Vo as your voltage gain, right? If combined question is there in the AC analysis, mid frequency voltage gain is nothing but Vo divided by Vi. That is true, but we don't have to incorporate that particular value of Vo divided by Vi in your CMI calculation, because this R signal will give you some voltage drop and that will give you the wrong answer for CMI, right? So considerably small answer, small value of CMI we will be getting in terms of pico or nano farad. Okay, and we'll have to just add these values. That will be one of the capacitor CI. Same will be happen at the output side. So at the output side we'll be getting CO is equal to CMO plus CE now and plus CWO. Okay, wiring output capacitor, Miller's output capacitor and collector to emitter capacitor that are connected in parallel, so we have to connect, so we just have to add these values of capacitance and we'll get to know that value of CO is nothing but the addition of all these three. So we will write that all this stuff. Okay, so as far as frequency is concerned, this will be your high cutoff frequency at the input side, and that is nothing but 1 upon 2 pi RC I, right? CI will be getting directly, and from here we'll be getting FHO is equal to 1 upon 2 pi R into CO. Question arises, what is R? We'll say that we'll do Namakaran for input side as Ri, we'll do Namakaran for output side as Ro, right? What will be the value of resistances? Resistances value is nothing but, we just have to look from this particular capacitance and we'll have to say that these resistances, we just have to look from here, this particular side, and we'll have to open this and we'll have to say that these are connected in series, these are connected in, it's a parallel connection, right? So RB parallel R pi parallel R signal. So let's have to check it. Ri is nothing but, I can say, Rb parallel R pi parallel R signal. Okay, now similarly at the output side we will be getting Rc. If load resistance is given, we have to incorporate this load resistance. If it is given, we will say that RL. Okay, so if RC and RL are in parallel, so we will take this into consideration. We will say that the value of Ro is nothing but Rc parallel RL. So in this way we have got the two values of FHI, that is these values, and this value, two values of FHI and FHO for higher cutoff frequency in the form of, then we'll be getting the exact higher cutoff frequency we have to consider at the lower side. This is again because if we consider the frequency response at the higher side, then we'll get to know that if we consider one is at here, this will be FHO and this is FHI. Okay, so we have got the value of FHI and FHO, and let's see, we'll just draw. And obviously if we consider this value FHI, then FHO, suppose here we have got the value of FHO. This is your FHO value, and here we'll say that this is your point that we'll be getting half power point, and here we'll be getting the AV divided by root 2 and AVO divided by root 2, I can say, if we consider FHO. And if we consider this FHI, then we'll be getting the higher value of gain, and that's what we want. If we check with another ink, then we'll get to know that this is something different. Okay, so here we can say that whatever gain we will be getting, that is AVI divided by root 2, considering the fact that FHI, then we'll get the higher gain, and that's what we want, and that is nothing but my aim of amplification. So if we consider the lower side, then that will be beneficial as the circuit worked as another amplifier. So we will say that we will choose the frequency FHI over here, right? But not always. We have to calculate the value of FHI and FHO. We have to consider the value of FH, that is higher cutoff frequency, as minimum value out of these two values, that is FHI and FHO, right? So we will take more and more examples regarding the higher frequency response of BJT amplifier as well as FET amplifier, and then we'll move towards the numericals of Mumbai University examination. So stay tuned for those videos. Learn more and more Ekeeda, learn more and more EDC with me. Thank you so much.